Okay, here in example 1, we have the function f of x is equal to 2 raised to the x minus 1 power. One thing I want to point out just real quick is that the 2 represents the base. That is not a vertical stretch. That is telling you what the parent function is, namely that the parent function in this particular case is 2 to the x. Now, what does the minus 1 do in the exponent? You can think of that as being inside the function, and so inside means horizontal, and so therefore this is going to move the graph to the right one, which is going to change all of my x coordinates by adding 1 to them. So this is going to be -1, 0, 1, 2, and 3. Okay, so going ahead and plotting these points, -1 and 1/4 is going to be about there, 0 and 1/2, right there, 1, 1, 2, 2, and finally 3 and 4. And so you can see that this graph, we didn't move it up or down, so that horizontal asymptote is still going to be at y is equal to 0. And that was pretty close. I nearly made it through all of those points, not bad. And so let's go ahead and talk about some of these characteristics. First of all, the domain is -infinity to infinity. You're touching every number on the x-axis. The range starts at 0 but does not include 0 because of the asymptote and goes to infinity. This is a continuous function, as is every exponential function. They're all going to be continuous. This particular exponential function is increasing on its entire domain, -infinity to infinity. This is bounded below, because you can see that I could draw a horizontal line below the graph, and so it's bounded below. Let me finish writing my word there. There is no extrema, there's no symmetry, there is an asymptote, this time a horizontal asymptote at y is equal to 0 in this particular case, and my end behavior is going to say the limit as x approaches infinity of f of x. So as we look at the right end of the graph, the y values are increasing without bounds, so they go to infinity, and the limit as x goes to -infinity of f of x. Well, as you go to the left, this graph is approaching the y coordinate 0, and so this left end behavior limit is going to equal to 0. Okay, here on example 2, we have 2 to the -x power, and so once again, my parent function is going to be 2 to the x, which is why I have the table of points right here. And then what's happening to this graph with that negative that's in the exponent? That negative in front of the x means that this is a reflection over the y-axis. And so what that's going to do is it's going to change the sign of all of our x-coordinates to the opposite sign. And so what that's going to do to the graph is it's going to make it not increasing anymore, but decreasing. And so if you start plotting these points, 2 and 1/4 is going to be here, 1 and 1/2 will be here, 0, 1 right there, and then -1, 2 is here, and -2, 4 will be right there. And so you can see this is still going to have a horizontal asymptote at y equals 0. And this time it is going to be a decreasing function through those points and then approaching that horizontal asymptote. And so what is my domain? -infinity to infinity. My range, once again, even though it doesn't look quite the same, it's still going to be 0 to infinity, because remember, we read the range from bottom to top. This is a continuous function. This time, though, the function is decreasing from -infinity to infinity. This looks a lot like an exponential decay model, and I'm going to explain why that is here in just a minute. It is bounded below, just like before. There is no extrema, no symmetry. There is a horizontal asymptote at y equals 0, and then my end behavior, I have the limit as x approaches positive infinity of g of x. That's going to equal to 0, since at the right end of the graph we're approaching 0, and the limit as x approaches negative infinity of g of x is going to equal to positive infinity. Now, why does this look like an exponential decay? because 2 to the negative x is really the same thing as 2 to the negative 1 raised to the x power. Well, what is 2 to the negative 1? Whenever I have a negative exponent, that just means to take the number down to the denominator. And so this becomes 1 over 2 to the x. And so you can see there that in that particular form, this is an exponential decay. So it's just a different way to write 1/2 to the x power. So hopefully that makes sense. If you have any questions about that, please feel free to reach out to me with that. I didn't mean to confuse anyone with that, but I did want to show you why this graph looks like an exponential decay, why it's decreasing, and it just has to do with these exponential properties and these exponent rules that I've displayed over here. Okay, here on example 3, we've got a 3 in the front of our function 2 to the x, and so again, this is going to be base 2, which I've written the points out for a base 2 graph right here, and this time we're going to have a vertical stretch by a factor of 3, and so that means I'm going to multiply my y-coordinates by 3, so that this becomes 3/4, this becomes 3/2, 3, 6, and 12, and so this is going to basically just make my graph even faster of a growth than normal. So -2 and 3/4, -1 and 1.5, 0 and 3, 1 and 6, I think that's 6, and then 2 and 12 is actually going to take me all the way off the graph. And so once again, there's my horizontal asymptote at y is equal to 0. And this graph is going to be increasing because that base is bigger than 1. And it's going to go through my points here and get very, very tall very fast. And that's a technical term, getting very tall very fast. It is a very fast growth, exponential growth. One of the fastest growths that we have of any of our functions. These y values get big really fast. And so again, just jumping into some of these characteristics, my domain will be -infinity to infinity. My range, 0 to infinity. It is a continuous function. This time it is an increasing function on its entire domain. It is bounded below. Once again, as you can see, we can draw a horizontal line below the graph. There is no extrema, there's no symmetry. There is an asymptote, a horizontal asymptote at y is equal to 0, and my end behavior limits. And really, guys, the reason I continue to write these limits, even though they're pretty much the same on every problem, is that we're continuing to struggle writing these limits, and so I want to just give you more practice with that, just writing in this notation. So that left end behavior is 0 because we're approaching 0 on the y-axis as x gets really negative. Okay, here on the last example, again, e to the 2x. I'm not going to worry too much about plotting an exact ordered pair for each item, but here I do want to notice that this 2x there in the exponent, that is a horizontal shrink by a factor of 1/2, and so that's not going to really do anything to the function. This is still going to be an exponential growth. It's still going to have a horizontal asymptote at y equals 0 since we're not moving the graph up or down, and it's still going to go through the point 0, 1. And so this is going to be an exponential growth that goes through that point 0, 1 and then grows very quickly like so. And so again, what is our domain? -infinity to infinity. What is our range? Starting at 0 but not including 0 and going to infinity. This is a continuous function. It is continuously increasing on its entire domain, -infinity to infinity. It is bounded below, just like every other exponential function has been bounded below. There's no extrema, there's no symmetry, there is an asymptote at y equals 0, and there is end behavior with a limit as x approaches infinity of f of x equaling to positive infinity, and a limit as x goes to -infinity of f of x and that equals to 0. And so if you guys have any questions on graphing exponential or logarithmic functions, please let me know, and just keep in mind that they are inverses. And so when you're creating those tables, remember that all you have to do, if you know the logarithm, all you have to do is switch the x and the y in order to get the exponential. You guys have a good day, and we'll talk to you soon.